Imagine that tonight you look up at the sky and see the moon hanging there, soft, gentle, glowing quietly in the dark. Now, instead of standing on Earth, try placing yourself right on the surface of the moon, in a distant, frozen place of absolute silence. There is no air to carry sound, no cars, no wind, no voices. Only the blackness overhead, and beneath your feet a vast gray landscape stretching endlessly, speckled with rocks and ancient impact craters. Above the curved horizon, Earth appears like a small blue jewel suspended in space. From this faraway place, your world looks tiny, and yet impossibly precious. And if you look just a little longer, you begin to sense that the moon isn't a flat picture painted onto the night sky, but a real world of its own, harsh, unyielding, and undeniably alive in its stillness. In imagination and in poetry, the moon is often painted as a gentle companion, a friend who softly lights up quiet paths. But when we step into the language of science, we start to realize that behind that silver beauty lies an environment that is anything but friendly. The air is almost non-existent, turning every breath into something utterly dependent on life support systems. The pressure is so low that without protective layers, the human body simply couldn't survive. Cosmic radiation and solar wind sweep across the surface unchecked, falling like an invisible storm. Temperatures swing from blistering heat to biting cold, rising and plunging with a strange, drawn-out day-night cycle. Across its surface, there are few places anyone could call comfortable. And yet, amid all these dangers, one question still lingers. Is there a true, deadly zone on the moon? A place where the harshest conditions gather? A realm so extreme that both humans and machines must tread with utmost caution. When scientists speak of the most dangerous place on the moon, it isn't a dramatic phrase meant to grab attention. It is a concept grounded in very specific physical conditions. Temperatures dipping toward the limits of what materials can withstand, intense radiation, treacherous terrain, constant micrometeorite threats, and especially those permanently shadowed regions where sunlight has never touched. Such places often lie deep within craters near the poles, where the floors have remained in darkness for billions of years. Inside those shadows, temperatures drop so low that most normal electronics would fail unless engineered with extraordinary care. Simply keeping batteries, circuit boards, and lubricants warm becomes a major challenge. Any energy source that depends on sunlight becomes useless. Missions must rely on nuclear power or other complex alternatives. For humans, this is a place where even the smallest flaw in a spacesuit or shelter could become fatal in an instant. And yet, in a quiet twist of irony, these harshest places may also hide some of the moon's most valuable scientific treasures and resources. In that eternal darkness, water ice can remain preserved for billions of years without evaporating. Alongside it may be rare elements, traces of ancient geology, and clues about the early history of the entire solar system. So when we speak of a deadly zone on the moon, we are not only talking about danger in the literal sense, we are speaking of a threshold of knowledge. If we can conquer it, humanity gains access to water for life, oxygen to breathe, rocket fuel for deeper journeys, and scientific data that may illuminate the origins of Earth, the moon, and even ourselves. But if we fail, the cost could be lost missions, abandoned equipment swallowed by the dark, or even the lives of the first explorers bold enough to venture there. Imagine standing at the rim of a deep crater near the South Pole, where sunlight grazes the outer edge for only a brief moment, while below lies a bottomless sea of darkness. Behind you hangs the soft blue glow of Earth. Before you yawns a frozen abyss where temperatures fall to almost unbelievable lows. This may be the boundary between a relatively safe zone and a true deadly land. One step farther, and you are staking your life on humanity's hunger for understanding. From that vantage point, the moon is no longer a gentle silver glow in the night sky. It becomes a vast examination of our ingenuity, our patience, and our will. Every mission plan, every spacecraft, every spacesuit, every line of code guiding a robotic explorer must be crafted with the awareness that this environment offers no forgiveness. And still, after all of that, this deadly land remains there, quiet, unmoving, yet somehow calling out. Both threatening and inviting, it seems to whisper the simplest, most profound question. Are we truly ready to step inside? The echo of the previous chapter lingers, like a long, gentle breath drawn across the vast darkness of space. As the story of the moon's deadliest land begins to unfold, the surroundings sharpen into focus, as if a thin veil of mist has quietly lifted to reveal the true nature of this pale, silvery world. Seen from Earth, the moon always appears so calm it seems almost frozen in place. But if we describe it through the objective truth of science, it becomes an entirely different world, one so unforgiving it borders on unbelievable, a place where natural life cannot arise, a celestial body stripped of every condition familiar to humans. There is no atmosphere to soften the sunlight, no blue sky to cradle the horizon, no wind, no liquid water, no sound carried through the air. Only a perfect emptiness, wrapping around every grain of gray dust like a cold blanket stretching all the way to the curved edge of this small world. If you stood on the moon during the day, you would witness a scene so strange it feels contradictory. The ground blazes under sunlight that cuts straight down like a sharp blade. Yet above your head, the sky remains pitch black, blacker than any night you have ever seen on Earth. The atmosphere is far too thin to scatter light. So even as the sun burns overhead, the sky refuses to change color. On the moon, sunlight doesn't soften as it filters through air. It slams directly onto the ground, unfiltered, undiffused, raw and indifferent in its pure physical force. When darkness falls, that world plunges instantly into a night so absolute it borders on total. There are no city lights, no atmosphere reflecting the faintest leftover glow. Nothing but pure darkness and stars sharp as needles pinned into space. The light-dark cycle stretches in an almost surreal way. It takes about 29.5 Earth days to complete a single lunar day. That means the moon endures 14 days of relentless sunlight, followed by 14 days of bone-deep cold. This slow rhythm drives extreme temperature swings. The surface can heat to over 100 oxylar during the day and sink below 150 once night settles in. There is no in-between, no atmosphere to ease the transition, no gentle cushion between scorching heat and cutting cold. In an environment like that, even gravity becomes part of the strangeness. Lunar gravity is only about 1/6 that of Earth. Every object, every step, every movement becomes weightless, as if the entire space around you is operating by a different rulebook. Humans can leap higher, farther, drifting as though floating. But living long-term in low gravity introduces a quieter challenge. Muscles weaken, bones grow brittle, and the body struggles without the natural compression it evolved with for millions of years. A sustained lunar habitat would have to constantly compensate for this through exercise devices and biological support systems. Look deeper into that landscape, and you'll realize that the moon's silence doesn't bring the familiar peace of an earthly night. It is a silence of totality, the silence of a place that has never known life. No wind, no water, no leaves trembling, no insects whispering. All that remains are vibrations traveling through solid ground when impacts occur, gentle tremors that never travel far. The world appears still, yet it hides danger everywhere. Sunlight without atmospheric shielding becomes an invisible wall of fire, burning anything exposed to it. Long stretches of night freeze the surface so intensely that some metals begin to turn brittle. With almost no magnetic field, cosmic radiation can strike the ground unhindered. Tiny electrically charged dust grains may hover in the thin exosphere, clinging to every surface, slipping into every crack of any machine. In a place defined by absolute stillness, even the smallest motion becomes hazardous in a rhythm untouched for billions of years. The moon makes no sound, yet it holds the scars of every blow it has ever taken since the solar system's formation. Craters large and small lie scattered across its surface like ancient wounds, telling stories of a chaotic era when cosmic debris rained down relentlessly. On Earth, weather and geology have erased most traces of that past, but on the moon they remain perfectly preserved, a silent archive of history. And through all of this, one truth remains impossible to ignore. Humanity still dreams of coming here, staying here, and learning to live with its challenges. The first footprints have already touched its dusty surface, but the road ahead is far longer and far more complex. The moon does not welcome anyone gently. It offers no comforting wind, no warm atmosphere, no soft touch of nature. Only silence, harshness, and difficulties scattered across its terrain. But that very silence creates a strange allure. In this soundless darkness, humanity senses an opportunity to learn, to explore, to understand more deeply the history of the cosmos. The moon, gentle as it appears from Earth, is in truth a grand examination, a wild, untouched world where life has never taken root. And to conquer it, we must agree to face every hidden danger lying just beneath its gray dust. And so, once we grasp the severity of this environment, the next question slowly takes shape. If this is only the broad picture, then what awaits in the deepest, coldest shadows? The regions known as the most dangerous places on the entire moon. In that stillness, where the moon reveals its raw, untouched nature preserved over billions of years, every environmental factor seems pushed to its limits. And once we understand the severity created by its structure and near-absent atmosphere, the next part of the story naturally unfolds. It is precisely this lack of a protective layer that turns temperature on the moon into one of the most dangerous challenges humanity has ever faced. Temperature on the moon is not simply a matter of hot or cold. It is an extreme dance between two opposing ends, unfolding slowly but mercilessly, always ready to test any system or living being that dares to stand on its surface. When sunlight strikes the gray regolith directly, its energy is not softened or scattered by an atmosphere the way it is on Earth. Instead, it crashes straight onto the ground, driving temperatures up to around 120 degrees Celsius. That is hot enough to melt certain plastics, damage unprotected electronics, and heat metal surfaces until they burn like a sheet of glowing steel. On Earth, you may feel stifling heat in the summer, but the atmosphere always filters the sunlight to some degree. On the moon, that softening simply doesn't exist. Sunlight falls pure, unfiltered, and absolute, but heat is not the only ruler here. When the sun slips beneath the horizon and the long lunar night arrives, temperatures plunge into a realm of brutal cold. With no air to hold on to even the faintest trace of warmth, the moon's surface becomes like a massive stone left out in eternal winter. Temperatures fall rapidly to around 130 degrees Celsius, cold enough to freeze most liquids instantly. At such extremes, metals grow brittle, lubricants solidify, and mechanical systems face the threat of total shutdown. A human without proper protection would lose heat so quickly that survival becomes nearly impossible. This contrast does not unfold gently or gradually. In the transition zones between sunlight and shadow, the lunar dawn and dusk, temperatures can shift dramatically within just a few steps. One spot still burns under direct light, but crossing into the neighboring patch of darkness, the temperature can drop by dozens of degrees in an instant. For robots or astronauts, a single misstep can transform a relatively stable environment into a sudden, severe challenge. Apollo astronauts once described these light-shadow boundaries as invisible dividing lines, where every step carried a sense of uncertainty. Yet the cold of lunar night is only the beginning. Near the poles, deep inside enormous craters that sunlight has not touched for billions of years, temperatures reach the extreme limits of physical reality. 250 degrees Celsius to 240 degrees Celsius, roughly 20-30 Kelvin. These are some of the lowest temperatures recorded anywhere in the solar system, cold enough that nearly all materials can be damaged simply by contracting too much. These permanently shadowed regions at the moon's north and south poles are natural chambers of near absolute cold, places where any device not purpose-built for such conditions would freeze, crack, or fail within moments. Because of this, human survival on the moon becomes a technical puzzle of extraordinary complexity. A spacesuit isn't just a protective layer. It is a miniature ecosystem designed to keep the human body stable while the environment constantly tries to drag it toward two opposing extremes: heat intense enough to burn skin, and cold harsh enough to shatter cells. The suit needs thick insulation, active thermal control, heat-reflective materials to shield against harsh sunlight, and cooling systems to prevent the wearer's own body heat from building up. At the same time, it must retain warmth when needed, preventing heat loss during long stretches in shadow. Future lunar shelters will follow the same principle. Many imagine that moon homes will be built partially beneath the surface, using regolith as a natural insulating blanket to stabilize indoor temperatures. Others envision habitats placed in permanent shade, where sunlight never strikes directly and temperatures stay more stable. Such living spaces will require strong cooling systems during the 2-week lunar day and continuous heating during the 2-week lunar night. Crucially, every system must be both reliable and redundant. A single flaw in thermal design could lead to serious consequences. All of this turns lunar exploration into a journey that demands careful planning. Not only must technology be ready, but humans must be mentally prepared to face a world where temperature never allows for carelessness. Yet within this harshness lies a strange beauty. The moon is not gentle, not soft, not the poetic image we often project onto it. Instead, it is a world of certainty, unyielding, direct, and honest about its physical nature. The moon hides nothing. No atmosphere to paint an illusionary sky. No moisture to diffuse the light. No life to disturb its ancient rhythms. There is only the switching of heat and cold, of brightness and darkness, of stillness and severity. And once we understand this extreme thermal portrait, the next question becomes obvious. Beyond these temperatures that rise and fall like a fierce cosmic symphony, what else lies in wait within the moon's silent environment? The invisible radiation from the sun and the galaxy will be the next threat ready to be revealed. Amid those unforgiving temperature swings, the moon reveals the stark indifference of a world stripped of every natural layer of protection. And when we look more closely, that very bareness leads us to a danger subtler than heat or cold. A threat without shape, without sound, unseen yet ever present across the moon's pale, silvered surface. Cosmic radiation on the moon is a peculiar kind of hazard. It makes no noise, leaves no immediate mark, yet slowly seeps into every material, every cell, every piece of equipment. Earth is fortunate. Wrapped in its ozone layer and vast magnetosphere, it carries a giant protective umbrella that blocks most high-energy particles from the sun and the galaxy beyond. But the moon has nothing of the sort. With almost no atmosphere, almost no magnetic field, its surface lies exposed beneath a constant storm of energetic particles, like a sheet of metal placed inside the universe's natural radiation furnace. These rays can pass straight through soft tissue, break apart DNA structures, and trigger changes that cannot easily be undone. An astronaut on the moon cannot avoid them simply by stepping into the shade. Radiation doesn't care about shadows or sunlight. It comes from every direction, from the solar wind to high-energy particles hurled across the galaxy by distant supernovae. Direct measurements show that the moon's surface receives about 60 microsieverts of radiation per hour. A number that sounds small, but is actually more than 200 times what you typically experience per hour on Earth's surface. Within just 24 hours, an astronaut's body could absorb nearly as much radiation as a full year of normal living on Earth. Continue that for days or weeks, and long-term damage becomes unavoidable. And on the moon, background radiation is only the beginning of the story. The true danger comes from solar storms, eruptions of energetic particles powerful enough to disrupt radio signals on Earth and disable satellites in orbit. When such a storm rushes toward the moon, nothing stands in its way except the shelters humans build for themselves. Billions of high-energy protons pour down at nearly the speed of light. If an astronaut is working outside when the storm hits, without reaching a shielded shelter in time, one with heavy protective layers or a thick blanket of lunar soil overhead, they could receive a radiation dose high enough to trigger acute radiation sickness. Nausea, suppressed immunity, neurological impairment, and even the risk of death. For that reason, any future lunar base must include a radiation storm shelter, an area fortified with materials capable of absorbing harmful particles, or buried beneath a thick layer of regolith to reduce penetration. The thicker the shield, the stronger the protection. For astronauts, the most effective solution is often to hide beneath several dozen centimeters of lunar soil, whose metal-rich composition and natural density help absorb radiation. Yet building such a shelter poses major engineering challenges, requiring excavation, transport, and soil compaction technologies that must all function in low gravity. Beyond solar storms, even more powerful particles drift in from outside the solar system. Galactic cosmic rays. These particles are so energetic that no ordinary shielding can completely stop them, only lessen their impact. They can slip through spacesuit layers, punch into electronics, flip bits, damage chips, and trigger cellular mutations within the human body. Unlike solar storms, they are not explosive or sudden. They are a quiet, constant presence, day after day. The long-term health consequences for astronauts cannot be overlooked. Extended exposure increases the risk of cancer, damages the central nervous system, impairs cognition, and can cloud the lenses of the eyes, a problem documented in many astronauts who have spent months in space. The immune system, too, can weaken over time, leaving the body more vulnerable. In this context, Any dream of long-term lunar habitation, as inspiring as it may be, requires far more comprehensive radiation protection than the short Apollo missions ever needed. Spacesuits must carry thick radiation-resistant layers, yet remain flexible and light enough for movement in low gravity. New materials like hydrogen-rich polyethylene and advanced composite coatings are being studied to reduce exposure. Lunar-based designs must prioritize shielding as well, from covering habitats with thick mounds of regolith to building structures directly underground. Some concepts even propose using water as a natural radiation barrier, since water absorbs energetic particles well. This could be especially valuable in the polar regions, where ice deposits may serve both as a resource for life and a shield for safety. All of this makes the journey to the moon not just a meeting with a cold, barren landscape, but a confrontation with invisible forces woven through the cosmos. Radiation has no color, no sound, no recognizable face. Yet it stands among the greatest medical challenges space exploration must overcome. Understanding it, how it moves, how it interacts with life, how it erodes materials, is essential to safeguarding the first crews who will one day live and work on the moon for days, months, or even years at a time. And as we slowly come to accept radiation as a silent, persistent companion of the lunar environment, another question rises, like a new layer of mystery waiting to be uncovered. Beyond this invisible threat, what other dangers of space might strike the moon suddenly, swiftly, without warning? The answer lies in the tiny stones racing out of cosmic darkness, the micrometeorites that stalk the moon's quiet surface forever unannounced. Amid the invisible streams of radiation quietly drifting through the moon's silent expanse, it's easy to imagine that no threat could be more delicate or more elusive. But in truth, when radiation is only one chapter of the story, another danger lurks from every direction in the cosmic dark, striking so swiftly that no one could ever see it coming. On Earth, the thick atmosphere wraps our planet in a natural suit of armor, burning up billions of tiny meteoroids each day without our ever noticing. Shooting stars, those graceful streaks across the night sky, are merely the beautiful surface of a powerful protective process. The moon, however, is granted no such luxury. Its almost non-existent air cannot create friction, cannot slow an incoming object, cannot burn anything away. On the moon, even a fleck of cosmic dust smaller than a pea becomes a miniature bullet, traveling fast enough to pierce metal. Over 15 years of observations, instruments have recorded more than 400 meteor impacts on the lunar surface, each impact triggered by objects weighing only a few dozen grams. The frightening part is that these collisions don't resemble stones dropping onto soil. They resemble sudden punches from the void, silent, unannounced, with no sign of where or when the next one will land. On the moon, meteor strikes are not rare events. They are part of the natural rhythm of the lunar world. When people picture meteors, they often imagine massive rocks carving giant craters. Yet the true danger often comes from far smaller fragments. Micrometeorites, just millimeters in size, slam into the surface at tens of kilometers per second. At such speeds, even a tiny grain of dust carries the energy of a miniature explosion, enough to chip metal, puncture protective layers, or damage delicate equipment. In that context, an astronaut walking on the moon is exposed to these cosmic bullets, even if the chance of being hit directly remains low. But an even subtler danger lies beyond the micrometeorites themselves, the debris they send flying, ejecta. When a meteorite hits the lunar surface, it doesn't simply carve a small crater. It blasts out sharp fragments of rock that scatter across kilometers. These shards are not soft, not light, and can travel fast enough to become serious threats. They behave like secondary bullets, with unpredictable paths, capable of piercing equipment, damaging sensors, antennas, or solar panels. The troubling truth is that an impact occurring miles away can still endanger a lunar base that seems perfectly safe. Without an atmosphere, the moon offers no drag to slow anything down, no winds to shift its path. A piece of ejecta can fly far beyond what intuition suggests, creating a kind of ever-present hazard, a natural firework of danger that could erupt at any moment. And so the question emerges: how do we protect people and technology from a threat that is invisible, random, and impossible to predict? Future lunar bases will require multi-layered protective design. One of the most important ideas is to build overhead shielding with lunar soil, covering the habitat beneath a thick blanket of regolith. This layer not only protects against radiation, but also acts as armor, absorbing the force of micrometeorites and flying ejecta. It's much like carving out a bunker beneath the surface, a shelter against sudden blows from the cosmos. Spacesuits, too, must be built tougher than those used in low Earth orbit. Their outer layers must endure high-speed impacts from microscopic particles, yet remain light, flexible, and suitable for movement in low gravity. Engineers are studying composite fibers, ultra-thin metallic coatings, and multi-layer materials to withstand the violent speeds of micrometeorites. Some engineers have also proposed early warning radar systems to detect larger incoming meteoroids. While micrometeorites cannot be predicted, radar could identify bigger objects approaching the moon, giving astronauts precious time to take cover in shelters. Such a system would serve as a scaled-down counterpart to Earth's meteor monitoring networks, optimized for the moon's thin air and rugged terrain. Still, no solution can ever be perfect. The moon will always be a place where each passing second carries the possibility of a tiny particle hurtling out of the void. But that is simply the nature of living and working beyond Earth, accepting the risks the cosmic environment presents, and meeting them with human knowledge, technology, and careful preparation. When seen in full, micrometeorites and ejecta are just one part of the gauntlet humanity must pass to truly settle on the moon. And beyond these incoming bullets from space, another silent enemy waits, one that makes no sound, leaves no immediate wound, yet can wear down equipment, degrade spacesuits, and threaten human health in absolute silence. That enemy is lunar dust, a substance so small, yet so dangerous, that every plan for lunar settlement must treat it with utmost caution. The echoes of micrometeorites rushing in from the cosmic dark linger like a quiet reminder that the moon is a place that never stops testing human endurance. And just when we think those invisible bullets are danger enough, another enemy appears, not crashing in from above, but waiting beneath our feet, silent, slow, and more persistent than any other threat on this pale silver world. Across the lunar surface, dust exists everywhere, but it is nothing like the dust on Earth. Not soft, not gentle, not harmless. Lunar dust was born from billions of years of meteor impacts that crushed, scraped, and shattered basalt and anorthosite into tiny grains as sharp as broken glass. If you were to hold a handful of it, the first sensation wouldn't be softness. It would be the sting of its jagged edges, pointed like needles, eager to cling to any surface they touch. The Apollo astronauts encountered this dust directly, and they described it like an invisible attacker. When they returned to the module after an EVA, their suits were coated in dust, and as they removed them, the particles drifted through the cabin, slipping into their lungs, causing sneezing, congestion, sore throats. Some called it lunar hay fever, an allergic-like reaction triggered by a material completely foreign to life. Harrison Schmitt of Apollo 17 experienced a strong reaction that he detailed in mission reports. The scariest part wasn't the immediate discomfort, but the unanswered question hanging behind it. If just a few hours of exposure could trigger such a response, what would happen to someone living on the moon for weeks or months? And dust does not only threaten people, it is a formidable enemy of machinery. Particles smaller than 20 micrometers, 50 times thinner than a human hair, can slip into any gap, any joint, any rubber seal. During the Apollo missions, the soles of spacesuits were noticeably worn down after only a few hours of walking. Some sample containers lost their airtight seals because dust had worked its way inside. And when dust settles on electronic equipment, the risk of short circuits rises, a danger that could threaten an astronaut's life. There are still mysteries about lunar dust that modern science is trying to unravel. In low gravity, the dust lingers longer in the airless space near the surface, spreading farther and hitching a ride with astronauts into their habitats. When inhaled, these tiny particles can reach deep into the lungs, becoming lodged in tissue and causing long-term inflammation. Experiments using lunar soil simulants suggest that dust can destroy lung cells and even damage nerve cells under prolonged exposure. This raises concerns that people working on the moon for extended periods may face risks of chronic lung disease or cancer in the future. But lunar dust holds another strange quality, one that makes it behave almost like something alive: electrostatic charge. Because the lunar surface is constantly bombarded by the solar wind, dust particles become positively charged. This gives them the ability to lift off the ground and hover slightly above it. At lunar sunrise or sunset, the electric field between light and dark regions becomes so strong that it can raise dust into a faint, shimmering haze, an electrostatic dust storm that many instruments have recorded indirectly. From a distance, such a scene might resemble a delicate, glowing veil. But for humans and machines, it's a silent threat. Dust slips into robotic joints, blankets solar panels, clings to the visor of an astronaut's helmet, blocking light and clouding vision. It infiltrates machinery, creates friction, clogs moving parts, and shortens the lifespan of delicate components. In an environment with no wind and no rain to wash anything clean, wherever dust settles, it tends to stay. To confront dust, one of the greatest challenges of lunar settlement. Space agencies have spent years developing new ideas. Some propose coating spacesuits with nanolayers that prevent dust from sticking, or using electrically activated materials that gently vibrate to shake dust loose. Others suggest using electric fields to push dust away from critical surfaces. For example, solar panels could be covered with thin electrodes that, when activated, generate a field that sweeps dust away from the edges. Inside lunar bases, dust removal chambers will become essential. Before entering the habitat, astronauts may need to pass through a zone using air jets, electric fields, or vibrations to blow dust off their suits. Spacesuits themselves may be anchored outside the base using suit ports, minimizing the amount of dust brought indoors. Robots might explore the dustiest areas to reduce the need for astronauts to enter hazardous zones. Yet no matter how advanced the technology becomes, dust will always be part of the lunar experience. It can never be completely eliminated, only managed. And that makes lunar living not just a technological challenge, but a strategic one. How to endure in an environment where the tiniest enemy may be the most stubborn, almost eternal. And now, knowing that dust, something so small and seemingly harmless, has the power to slow the progress of an entire civilization. We must turn our attention to yet another risk woven into the moon's very landscape. Because beyond dust, heat, cold, and radiation, the terrain beneath our feet hides natural traps of its own, lying quietly in wait for the first pioneers who dare to step into this untouched world. Even though lunar dust creeps quietly into every corner, scratching machinery and threatening the health of astronauts, it is still only one piece of the immense puzzle this cold, silver world presents. And when that layer of dust is brushed aside, what emerges beneath is even more complex, as if the moon itself wants to remind us that its very structure, its shape, and its rugged contours are the most ancient challenges awaiting anyone who dares to walk upon it. The moon's terrain is often described as silent, yet within that silence lies a truth. Its surface is a vast, natural labyrinth. There are no gentle plains, no soft rolling deserts, no smooth horizons to guide the eye. Instead, every direction is marked by billions of years of relentless meteor strikes. These ancient scars never fade, because here there is no water, no wind, no weather to erode or soften the past. Every crater, large or small, remains stacked and overlapping like an endless geological record. Across the lunar highlands, craters may be just a few centimeters wide, or they may stretch for hundreds of kilometers. They appear so densely packed that from afar, the surface looks like metal hammered by millions of blows. Between them lie boulders, fissures, ridges, and irregular slopes, woven together into an unpredictable landscape. A single misstep could twist an astronaut's ankle on a sharp rock or send them stumbling into a dust-covered pit. And in low gravity, balance changes in subtle but dangerous ways, turning small mistakes into serious accidents. The ground itself is no ordinary soil. It is regolith, a layer of dust and shattered rock created by countless meteor impacts. In the highlands, regolith can reach depths of 10-20 meters, while in the younger basaltic mare, the dark seas visible from Earth, it is thinner, around 4-5 meters. The uppermost layer is extraordinarily porous, with up to 45% void space. This fragility comes from constant micrometeorite bombardment that churns the surface in the most literal sense. As a result, lunar ground is not as firm as rock. A heavy rover may sink into it like stepping into volcanic ash or dry powder snow. Rovers risk getting stuck, wheels may bog down, and astronauts can suddenly sink into pockets of ultrafine dust. Regolith is powdery yet angular, capable of digging into materials, increasing friction, and trapping anything that presses against it. Yet even these difficulties are only part of the story. The moon possesses a unique trait that complicates everything: extreme contrast between light and darkness. With no atmosphere to scatter sunlight, shadows become absolute. Under direct sunlight, the surface glows sharply like the flash of a blade. But in shadow, darkness becomes so deep it feels like a bottomless void. In such contrast, human perception falters. A deep crater may appear shallow. A large boulder may look like a harmless patch of shade. Apollo astronauts reported how difficult it was to judge distances or shapes, especially while driving across the terrain. A single miscalculation could send them plunging into what they believed was only a small, dark patch on the ground. Steep hills and cliff edges bring their own dangers. Many crater rims form slopes nearly vertical, rising tens of meters high. A lander touching down too close to such a rim risks tilting, sliding, or overturning. For astronauts, standing near a crater edge in low gravity turns every step into a calculated risk. With only 1/6 of Earth's gravity, losing balance becomes far easier. Gene Cernan once fell while collecting samples, a few meters more, and the consequences might have been far worse. But perhaps the most intriguing and perilous features of the Moon are hidden from plain sight. These are the ancient lava tubes, enormous subsurface tunnels formed during the Moon's volcanically active past. Molten lava once flowed through them, leaving behind hollow tubes when the outer shell cooled before the interior drained away. Over billions of years, many have collapsed, forming lunar pits, vertical shafts plunging tens of meters down. These caverns are both dangerous and full of promise. One step too close to the edge, and a person or robot could fall into a shaft they'd never escape. Inside, the darkness is absolute, the terrain unmapped, and every movement carries risk. Yet these tubes also offer stable temperatures, natural shielding from radiation, and potential shelter for future bases. They are like hidden rooms carved by the Moon itself, waiting silently beneath the surface for human discovery. Every crater, every layer of porous dust, every steep cliff and ancient lava tube tells a story about how this celestial body was shaped. But together, they also form a landscape filled with natural traps, a place where one wrong step, one misjudged distance, or one malfunctioning sensor could lead to serious consequences. And when we look at the Moon's rugged surface, one cannot help but wonder, is there a place even harsher than all we've described? The answer lies at the poles, where darkness never retreats, and cold reaches nearly absolute zero. There, a profound mystery waits to step into the light of human understanding. Even though lava caves and treacherous slopes reveal just a glimpse of the Moon's harshness, they are merely the doorway to even greater challenges. And once we step through that doorway, the sight that awaits in the polar regions makes every other place on the Moon seem strangely gentle, as if the journey is slowly leading us toward the very heart of cold and mystery. Near the Moon's south pole lies a place where sunlight rarely reaches, where time seems to stand still within an endless, hollow darkness. The Shackleton crater, spanning about 21 kilometers, one of the strangest and most captivating locations ever to draw human curiosity. From orbit, Shackleton appears as a massive circle, its rim gleaming under sunlight, while its interior is pure, absolute black. Half of its elevation model shows a jagged, rugged perimeter, while the real imagery reveals a darkness so dense it feels like staring into a bottomless well. Within that shadow, temperatures drop to unimaginable lows, cold enough to freeze everything: metal, plastics, even the most delicate electronics. The polar regions of the Moon possess a peculiar characteristic. Because the Moon's axis is almost perfectly perpendicular to its orbital plane, the Sun always hovers low near the horizon. This creates two opposite worlds separated by only a few steps. High peaks bathed in nearly constant light, and deep craters that have not seen sunlight for billions of years. These permanently shadowed regions, a name that sounds mythical yet is entirely real, can reach temperatures below 200 degrees Celsius, and at some of the coldest points, down to 240 degrees Celsius. At such extremes, most mechanical materials become brittle and crack, lubricants solidify, and solar panels lose all usefulness. A human being without perfect shielding would survive only a few seconds. And yet, that darkness carries more than danger. It holds the oldest secrets of the solar system. Because sunlight has not touched these craters for billions of years, the intense cold acts as a vast natural freezer. Every molecule of water evaporated from other regions of the Moon, every grain of ice carried by comets, every volatile compound drifting through space could fall into these pits and remain preserved forever. For this reason, scientists believe Shackleton and other polar craters may contain significant deposits of water ice, the single most important resource for any long-term lunar settlement. But in that absolute darkness, exploration becomes a challenge unlike any before. Robots or humans entering Shackleton's depths would have to operate in an environment where the only visible light comes from their own equipment. This darkness is not like Earth's night sky with its faint starlight. It is total, consuming, as if every beam is swallowed whole. Navigation becomes extraordinarily difficult, and every step feels like entering a primordial world untouched by any living being. If the shadowed craters symbolize danger and the extremes of cold, then not far away lies their opposite, the peaks of eternal light. Certain high points, such as Shackleton's Rim or areas near the Peary crater, receive sunlight almost year-round. Here, the sun rises low but rarely sets fully, creating a nearly continuous supply of solar energy. This is why these peaks are prime candidates for solar power stations, providing electricity for bases and exploration missions. The idea of building a base on Shackleton's Rim, where continual sunlight lies just steps away from ice-rich shadow, has become a breakthrough concept in lunar exploration. A base built on the eternal light could enjoy abundant energy while being only a few kilometers from the vast stores of ice below. Robots could extract ice and transport it upward while humans supervise from the safety of the sunlit ridge. This combination of perpetual light and perpetual dark creates a unique exploration ecosystem, a meeting point between extreme danger and boundless opportunity. From a scientific perspective, the South Pole is a treasure chest of knowledge. If large quantities of water ice are found, they could answer profound questions. Did lunar water originate from comets? From interactions between solar wind and lunar rock? Or from ancient internal processes within the moon itself? Any organic compounds trapped within the ice may hold clues to prebiotic chemistry across the solar system, and particles preserved in this cryogenic environment may contain traces of billions of years of history long erased elsewhere. Yet the South Pole demands absolute respect for the limits of technology. Temperatures of 240 degrees Celsius require every material to be redesigned. Heating systems, cables, even the software controlling robots must adapt to operating in continuous darkness. A robot descending into a shadowed crater needs more than light. It needs awareness that a single small mistake could leave it stranded forever. And so, in the grand view, Shackleton is more than a crater. It is a symbol of perfect contrast, where light meets darkness, where the coldest place borders a source of endless energy, where absolute danger exists alongside extraordinary promise for humanity's future. It is this very contrast that makes Shackleton one of the most dangerous, yet most beautiful, mysterious, and full of potential places on the moon. And as the South Pole begins to reveal its secrets, the story of lunar exploration moves forward once more, drawing us toward the most important treasure of all: water. Though the South Pole, with its eternal darkness, feels like a world set apart, mysterious, frozen, and suspended in time, it is there that the most important clue of all begins to reveal itself. And as the image of Shackleton opens in our imagination, the next question rises almost on its own. If the darkness preserves what the moon has long lost, could it also hold traces of the one thing humanity seeks most: water? For decades, the moon was considered a barren world, dry to the point of impossibility. The rocks and soil brought back by the Apollo missions showed no signs of liquid water, and for a long time, many scientists believed that the lunar surface was essentially devoid of it. But science always urges us to look deeper, wider, and more patiently. When modern orbiters began scanning the moon with more sensitive instruments, something surprising appeared. Unusual hydrogen signals clustered near the poles. Hydrogen is not direct proof of water, but it is a strong hint that water ice may be present. Missions such as Lunar Prospector and the Lunar Reconnaissance Orbiter repeatedly detected hydrogen concentrations inside permanently shadowed craters. The story of lunar water shifted from unlikely to worth investigating, and with that shift, a hopeful yet extremely cautious search began. The turning point came in 2009 when NASA conducted the El-Cross mission, one of the boldest experiments ever carried out on a celestial body. Instead of observing from afar, NASA sent an unused rocket stage crashing into the Cabeus crater near the South Pole, creating an artificial impact to blast material from the crater floor into space. The plan was like using a giant shovel to dig into a place humans could not touch directly. The results exceeded every expectation. In the plume of dust thrown upward by the collision, instruments aboard the trailing spacecraft detected clear signs of water vapor and tiny ice particles. Analysis revealed that roughly 20% of the material in the plume consisted of water ice and volatiles, such as methane, ammonia, and carbon dioxide. El-Cross didn't just confirm the existence of ice, it showed that water might exist in substantial quantities, enough to be considered a real, usable resource. This naturally leads to the next question. How much water does the moon hold, and where exactly is it? Neutron data show that hydrogen is distributed unevenly. Some regions contain concentrations so high, they've been described as ice pockets, while others are nearly empty. Many permanently shadowed craters are promising, but not all contain valuable deposits. Some estimates suggest the total amount of frozen water at the poles could reach hundreds of millions of tons. Shackleton alone, the central focus of the previous chapter, may hold tens of millions of tons of ice mixed into its soil. If these estimates are correct, they could transform the future of space exploration. In space, water is not only the foundation of life, it is the foundation of engineering. Every liter of water transported from Earth to the moon costs tens of thousands of dollars. If humans can harvest water where they intend to live, the moon becomes more than a short-term destination. It becomes a gateway. Water can be split into oxygen for breathing and into hydrogen and oxygen for rocket fuel. Imagine a future where ice mining stations operate in eternal darkness, melting frozen blocks, filtering impurities, and delivering water to reservoirs on the sunlit rim above. Water becomes the lifeblood of every system, providing air, creating fuel, cooling equipment, even serving as a protective shield against radiation. In that future, the moon is no longer just a place to visit. It becomes a place to live, to work, and to prepare for voyages farther outward, perhaps to Mars. But water's value goes far beyond practicality. Lunar ice is also a kind of time machine. Any water molecule that fell into the shadowed craters has been preserved almost unchanged for billions of years. Isotopic analysis of this ice can reveal whether lunar water came from comets, asteroids, or chemical reactions between solar wind and oxygen in the regolith. Such information helps reconstruct the history of water in the entire solar system, a mystery tied closely to the origins of life. And if those icy grains hold traces of simple organic molecules, the building blocks of prebiotic chemistry, the discovery would be even deeper. It could offer clues about how the earliest materials combined to form life. Some theories suggest that life on Earth may have been seeded by water-rich, organic-bearing objects. If the moon preserves pieces of that story, it becomes an invaluable natural archive. Yet reaching that water requires confronting the permanently shadowed regions, places near absolute zero, places without light, where every movement must be calculated with precision. The search for lunar water is not merely a hunt for resources. It is a test of human exploration itself. It demands stronger technologies, smarter robots, and bolder strategies. And as the picture of lunar water grows clearer, another question emerges. How can humans actually enter these regions of eternal night, operate robots, lift samples out, and survive the extreme cold? The answer leads us into the next chapter, where technology must face the absolute silence of the dark. Even though the traces of lunar water have opened new hope for future settlement, the path toward reaching those ancient layers of ice remains filled with challenges. And as it becomes clear that this precious water lies hidden within the moon's cold, eternal shadows, the next chapter naturally emerges. How can humans and robots step into the darkest, coldest, and most dangerous places on the entire lunar surface? The permanently shadowed regions are not merely deep craters near the lunar poles. They are places that have never seen sunlight since their formation billions of years ago. Chambers of cold so extreme that every familiar form of energy is silenced. In many ways, they are gateways to an alien world, where the rules of life as we know it on Earth no longer apply in any simple way. One of the greatest challenges for any explorer entering these shadows is energy. Without sunlight, solar panels, the main power source for most rovers, become entirely useless. A robot cannot draw power from pitch-black crater walls, nor capture a single ray of sunlight to fuel its systems. This forces engineers to design new power solutions. Large batteries, radioisotope thermoelectric generators, RTGs, or even long electrical cables stretching down from solar stations on the rim. Each option has strengths and weaknesses, and each requires careful planning. Without enough energy to keep its circuitry warm, a robot can freeze solid within minutes. Without enough energy to move, it can become trapped forever in darkness. And without enough energy to send signals back to Earth, the entire mission fades into silence, just like the darkness it set out to explore. The extreme cold poses another challenge. At temperatures between 200 degrees Celsius and 240 degrees Celsius, many metals become brittle, lubricants freeze completely, and mechanical joints can seize after only a few movements. This forces scientists to use special materials that require no lubrication, or to adopt dry joint technologies designed for the deep cold of outer space. Every component, wheels, brakes, hinges, and connectors, must survive conditions harsher than most Mars missions have ever faced. Venturing into the darkness also reveals another problem: navigation. Unlike sunlit regions, where cameras operate normally, permanently shadowed craters require rovers to see with far more complex artificial eyes. High-powered headlights are essential, yet even they are not enough to safely read the terrain. Rovers must combine them with LiDAR, 3D laser scanning, to map the darkness, identify rocks, slopes, subtle depressions, and obstacles invisible to ordinary light. Thermal sensors are added to detect areas that might contain ice or materials different from the surrounding regolith. Yet even with all these tools, every move must be taken with extreme caution. Hidden slopes can't be seen with the naked eye. Porous layers of dust can send wheels sliding, or worse, drop the rover into a pit too deep to climb out of. For humans, the danger grows even greater. If an astronaut were to descend into such a region, they would rely entirely on helmet lights and portable navigation instruments. Laying signal beacons from the crater rim deep into the interior would be essential, ensuring they can retrace their steps if visibility becomes compromised. There is no GPS, no sunlight, no natural landmarks, only a human facing an expanse of absolute black. To keep missions safe, teams on Earth must prepare with extraordinary detail. They must calculate every hour of rover movement, every moment of sunlight on the crater rim, every interval where Earth dips behind the moon's curve and communication temporarily drops. Planning includes not only routes, but also escape strategies, when the rover must return to light, when it must enter hibernation mode to conserve energy. NASA's Viper rover is a prime example of this complexity. Viper is programmed to run from the darkness, always keeping its solar panels within reach of even the lowest sun angles. A single mistake could let darkness swallow it, draining its battery and freezing it solid in just a few dozen hours. Because of this, mission planners have simulated every shifting shadow across an entire lunar day, mapping where sunlight will fall, where it will disappear, and exactly when. Another challenge emerges when the rover travels too deep inside a crater. Here, the crater walls can block all communication signals. Without a network of lunar satellites, no GPS, no lunar communications network, contact relies entirely on direct line of sight. Engineers must therefore choose craters that are not fully enclosed, or deploy relay devices along the rim to ensure communication is never lost. Navigation on the moon requires unique techniques as well. With no satellite guidance, the rover must rely on inertial navigation combined with terrain maps created from orbital data. This makes driving in permanent darkness a delicate challenge, where small accumulated errors can drift the rover off its safe path. All these factors combine to form one of the most difficult tasks humanity has ever faced in space exploration. The permanently shadowed regions are not just cold lands. They are places that test the limits of technology, endurance, and strategic planning. And once we develop tools strong enough to pierce that absolute darkness, another profound question arises. If we can retrieve samples from the moon's deepest, coldest places, what will they teach us? The answer lies in the journey of sample collection itself, the key to unlocking the history and mysteries of the moon we gaze at every night. Even though the permanently shadowed craters pose technical challenges unlike anything humanity has ever faced, reaching them is only the first step in a much larger story. And once we begin touching the moon's frozen soil, a natural question follows. Beyond water, what other treasures lie quietly beneath the pale regolith, waiting to be discovered? For decades, one idea has flickered in the background, a symbol of humanity's soaring energy ambitions: helium-3. The name may sound like a simple chemical label, but to scientists it carries the allure of white gold, rare, precious, and filled with the promise of reshaping civilization itself. On Earth, helium-3 is nearly non-existent, shielded away by our magnetic field from the solar wind. But on the moon, where no such shield exists, the solar wind has bombarded the surface for billions of years. Tiny particles of He3 have become embedded in lunar soil, accumulating over time into a reservoir humanity has yet to truly tap. The appeal of helium-3 comes from its extraordinary nature. When fused with deuterium, helium-3 produces immense amounts of energy with almost no radioactive byproducts, a dream that today's nuclear reactors still struggle to achieve. If such technology could be mastered, helium-3 could ignite a new era of clean, abundant, and safe energy. Some estimates suggest that just 25 tons of He3, a cargo small enough to fit in the payload bay of a shuttle, could power the entire United States for a year. Numbers like that inspire visions of lunar He3 mines becoming Earth's future lifeline. But the dream is far from simple. While lunar regolith does contain He3, its concentration is extremely low, just a few parts per billion. This means that to obtain even a small quantity of He3, humanity would need to process staggering amounts of soil. Roughly 1 ton of helium-3 requires processing nearly 100 million tons of regolith, enough to fill an entire valley. And extracting He3 demands heating the soil to around 800 degrees Celsius, releasing the trapped atoms from within the dust grains. The process consumes enormous energy and requires large-scale industrial machinery, furnaces, conveyors, reactors, essentially recreating Earth-like metallurgical plants on the Moon. These challenges place helium-3 mining firmly in the realm of future possibilities. Technologies for extraction, storage, and transport remain incomplete. Its economic viability is unproven, as every step, digging, heating, shipping, carries astronomical cost. On top of that, large industrial operations could disrupt lunar landscapes whose natural processes remain deeply mysterious. Yet helium-3 is only one small part of the Moon's resource landscape. Within every grain of soil and every rock, there is a long list of familiar elements essential to human life. Iron, aluminum, magnesium, titanium, all embedded within the regolith. Iron makes up about 14%, aluminum about 10%, magnesium 5%, and titanium around 4%, mostly locked in oxide form. These metals could be extracted and used to build structures, fabricate machinery, produce power systems, and support countless other needs. Titanium is especially valuable, lightweight, strong, and heat-resistant, and appears in high concentrations across many younger basaltic regions, such as the Sea of Tranquility, where Apollo 11 once landed. It could form ultra-strong alloys or radiation-resistant solar panels. Aluminum, ideal for electrical wiring and structural frames, is also abundant. And then comes the greatest surprise of all. About 40–45% of the Moon's soil mass is oxygen-bound within metal oxides. This means the Moon holds an immense reservoir of oxygen in its very dust. ISRU, in situ resource utilization. Technologies being developed by NASA and ESA aim to extract this oxygen through molten electrolysis or chemical reactions, creating breathable air and liquid oxygen for rocket fuel right on the Moon's surface. If successful, these methods could transform the Moon into a self-sustaining resource hub, harvesting water ice from the poles, extracting oxygen from the soil, refining metals from regolith, and even manufacturing parts from local materials. Humans could live on the Moon without relying entirely on supply shipments from Earth. A lunar base could become a stepping stone to Mars and deep space. But every ambition must be paired with responsibility. The prospect of lunar mining comes with an obligation to protect the space environment. Potential mines must avoid historical sites, such as Apollo landing locations. They must minimize dust plumes, avoid uncontrolled excavation, and ensure we understand the long-term impacts of altering the landscape. Helium-3 mining may remain a distant dream, but extracting water ice, oxygen, and metals to support lunar habitats could become reality within decades, opening a new chapter in humanity's life beyond Earth. And as resources start entering long-term plans, another critical question rises. Who will have the right to extract them? Who will manage the operations? Who will build the bases? And what laws will govern a place belonging to no nation? The journey from science to policy is beginning to unfold, opening a new chapter in the race to explore and regulate the moon. A chapter as tense as it is quiet. Wrapped in the very stillness of the celestial body humanity has watched since the dawn of time. Though the story of helium-3 and other precious lunar resources opens new horizons for the moon's future, all such dreams can only come true if humanity learns to survive using what the moon itself provides. With strict limits on what can be transported from Earth, self-sufficiency becomes the essential key to every long-term plan on this cold, silver world. From that perspective, a core question rises. Can the gray, seemingly worthless dust blanketing the moon become the foundation for humanity's future beyond Earth? On Earth, dust is a nuisance, but on the moon, it may be a strategic resource, the bedrock of the first cities beyond our home planet. The idea of turning dust into bricks comes from a simple need: building shelter. If we had to bring every brick from Earth, transportation costs would far exceed the capabilities of modern science. So engineers turned their attention to using regolith, the dust created by billions of years of meteor impacts, as a building material. Its particles are angular, rich in metal oxides, and naturally bond well under high heat. This led to a promising method: sintering regolith. In Earth-based experiments, ESA used lunar soil simulants and concentrated sunlight through parabolic mirrors to reach the necessary temperatures. What emerged were solid, durable bricks, sturdy as basalt. These made-on-the-moon bricks could be used to build landing pads, radiation shields, living spaces, and protective domes. Once perfected, this technology could transform the moon's entire surface into a vast supply depot, reducing the need for expensive shipments of construction materials from Earth. Beyond this, 3D printing technology opens an even more imaginative path. The idea is to deploy giant 3D printing robots on the lunar surface, machines that melt regolith with lasers or mix it with binders, then print entire structures layer by layer. Such printers could build towers, domes, radiation barriers, even habitats large enough for dozens of people. NASA has already shared designs for lunar homes, optimized for radiation shielding and stable internal temperatures. These structures demonstrate not just practicality, but the remarkable potential of building in a world defined by vacuum, cold, and extreme temperature swings. But construction is only one part of the self-sufficiency puzzle. Humans need oxygen to breathe, fuel to run equipment, and materials to craft tools, components, and infrastructure. Surprisingly, oxygen, a resource we once assumed to be scarce, exists in enormous quantities within lunar soil. About 40–45% of regolith's weight is oxygen-bound in metal oxides such as SiO2, Fe2O3, TiO2, and Al2O3. The challenge is simply to free it. The FFC Cambridge process has shown this is entirely possible. By immersing crushed regolith in molten salts at around 950 degrees Celsius and applying electrolysis, oxygen escapes as a gas while pure metals collect at the bottom. Experiments with lunar soil simulants have shown stable oxygen production and usable metal byproducts. A dual benefit: air for breathing and metals for building. Other chemical processes exist as well, such as heating ilmenite, FeTiO3, with hot hydrogen to create water. That water can then be split into oxygen and hydrogen, with the hydrogen reused in a closed-loop system. Such systems could run inside a lunar base, forming a self-sustaining life support cycle that requires only minimal supplies from Earth. However, true self-reliance cannot rely solely on inorganic materials. Humans need food, and fresh food is vital not only for physical health, but also mental well-being. Yet lunar soil is nothing like earthly soil. It contains shards of glass, heavy metals, no organic matter, and no beneficial microbes. Even so, early experiments have offered hope. When mixed with organics, fertilizers, and microorganisms, Apollo lunar soil samples have successfully grown lettuce and watercress. The plants were smaller and slower growing, but they grew, a powerful sign that life can take root in a place long considered lifeless. In the future, lunar greenhouses will use processed regolith as a planting substrate. The plants will help recycle astronauts' CO2 into oxygen, add a touch of green to the sterile environment, and provide fresh meals without needing transport from Earth. Such a closed-loop system could transform a lunar base into a miniature biosphere, supporting humans for months or even years at a time. One day, people may stand inside a lunar greenhouse, watching green leaves rise beneath artificial light, breathing air created from lunar soil itself, a future that suddenly feels not so distant. And once self-sufficiency becomes reality, a larger door opens. How will all of these activities, mining, construction, living, be governed legally on a world that belongs to no nation? The question of extraction rights, usage rights, and lunar law will become the center of the next chapter, where science intersects with politics and international treaties, in a realm silent yet filled with the ambitions of all humankind. Even though humanity's efforts to live off the moon's own dust and stone may one day help us build shelters, create oxygen, and perhaps even coax the very first green sprouts from its barren ground, there is still a deeper need, one far more profound than survival alone. It is the desire to truly understand what the moon is. And amidst all the technologies, plans, materials, and ambitions, the simple but essential truth is this: to understand our lunar companion, we must listen to the stories told by her own ancient stones. Among all methods of exploration, sample collection remains the single most important key to unlocking the moon's secrets. The rocks and soil may look like lifeless gray specks, yet every tiny grain is a fragment of a 4.5 billion year history. And every gram humanity carries home holds within it a story richer than any instrument could ever record from afar. For the first time in history, those stories came back to Earth in abundance through the Apollo program. A total of 382 kilograms of lunar samples, insignificant by the standards of factories on Earth, yet priceless in the realm of science, reshaped humanity's understanding of the moon's origin. Before Apollo, many theories coexisted. Was the moon a piece torn from Earth? Was it captured from elsewhere? Or did it form alongside our planet? Each idea had its logic, but the samples answered decisively in a way no one had expected. Geochemical evidence revealed that lunar rocks share oxygen isotope ratios strikingly similar to those on Earth, far too similar for the moon to be a captured outsider. Meanwhile, basalt samples from the lunar seas reflected signs of intense volcanic activity consistent with internal melting. Minerals found in highland soil dated back more than 4 billion years, older than any surface rock found on Earth. Together they formed a clear picture. The moon is likely the product of a colossal collision between the young Earth and a Mars-sized world known as Theia. That violent impact cast debris into space, and over time, those fragments gathered themselves into the moon, Earth's quiet companion for billions of years. This story might never have been uncovered without the Apollo samples, but that was only the beginning. Each sample brought home opened the door to new questions. Basalt from the broad lunar seas hinted that the moon once roared with volcanic fire around 3.7 billion years ago. Highland soil pointed to a primal ocean of magma that once covered the moon entirely in its earliest days. From her dust and stone, science began to understand that the moon's surface was never as calm as the gentle face we see from Earth. It once churned, boiled, melted, and cooled through an ancient era of fierce transformation. Then came lunar meteorites that fell to Earth, along with samples returned by the Soviet Luna missions and China's Chang'e 5. And with them, new surprises emerged. Chang'e 5 returned volcanic rock only about 2 billion years old, far younger than anything Apollo had ever revealed. This discovery suggested that lunar volcanism lasted billions of years longer than expected. The moon did not die as early as once believed. Its interior may have held on to heat far longer than anyone imagined. Furthermore, analysis of soil from the lunar poles revealed traces of water ice and minute organic compounds, tiny but essential pieces in the story of how water and organic matter spread across the solar system. This raised new questions. Did these molecules come from comets, from asteroids, or were they created in place through chemical reactions driven by the solar wind? And if they remained preserved in darkness for billions of years, could they become precious samples that help humanity understand the early chemical environment of the space surrounding Earth? These questions continue to push humanity forward in the quest for more samples. The 21st century is not an era of merely observing the moon through telescopes or remote robots. It is the era of returning, touching, and bringing back new evidence. NASA's Artemis program, with crewed missions aiming for the lunar South Pole, plans to collect at least 35 kilograms of samples on each trip, an enormous haul compared to most modern missions. These samples may include soil untouched by sunlight, potentially water-bearing materials, and darker, shadowed terrain, things Apollo never reached. Meanwhile, China's Chang'e 6, 7, and 8 missions are planning to collect samples from the poles and the lunar far side, filling in missing pieces of a global lunar sample map. International cooperation, or even simple sample exchanges, could rapidly expand research and deepen our collective understanding of Earth's silver-hued sister. Yet the future does not lie solely in returning samples to Earth. A farther but increasingly realistic vision is beginning to take shape in the minds of many scientists. Laboratories built directly on the moon. Instead of transporting tens or hundreds of kilograms of material home, scientists could analyze them on site, inside bases constructed from lunar soil itself. Initial data, mineral ages, chemical compositions, distributions of ice, could be measured right where they lie. Only the rarest, most scientifically valuable samples would make the journey back to Earth. In every scenario, each grain of dust, each stone, each scoop of soil carries the moon's long, unbroken story. A story no satellite, radar, or camera can ever tell on her behalf. And as those stories slowly come into focus, humanity takes one small step closer to truly understanding our planet's oldest companion. But alongside these pure scientific discoveries, another challenge has begun to grow. As more nations seek to land on the moon, to gather samples, to mine, to build, who will have the right to do what, where, and under what rules? The question of space law and sovereignty opens the next chapter, where the obstacles no longer come only from the moon's rugged terrain, but also from humanity's own soaring ambitions. Even though every lunar sample carries within it the story of billions of years of cosmic change, those stories do more than help humanity understand the past. They open a larger, more pressing, and deeply modern question. The more we understand the moon, the more clearly we see the treasures hidden within her. The more we must ask, who will be allowed to touch, to extract, and to claim those resources? And from this point, a completely new chapter of space history begins. a chapter about rights, laws, cooperation, and competition on a world that belongs to no one. For decades, humanity liked to imagine the starry sky as a clean, peaceful, pure realm untouched by the conflicts so common on Earth. But as we step closer to the era of space resource extraction, that serenity grows fragile. The moon, once merely a muse for poetry, has become the center of a new strategic race, where nations must confront one fundamental question: how can you use a resource without claiming sovereignty? That question begins with an old but essential document, the 1967 Outer Space Treaty. It states that no nation may claim sovereignty over the moon or any other celestial body. No one may plant a flag and say, "This part is mine." This principle created a foundation of equality among nations. However, the treaty does not forbid resource extraction. In other words, no one owns the moon, but anyone may take resources from it, a legal gap that opens both opportunity and the risk of conflict. In 1979, the Moon Agreement attempted to define lunar resources as the common heritage of humankind, requiring that all benefits be shared equally. It sounded idealistic, even noble, but most major powers refused to sign. They did not want to be obligated to share their hard-earned achievements with every other nation. From that moment, the question of space resource ownership fell into a quiet pause, waiting for the moment it would flare up again. That moment arrived in 2015, when the United States passed a law allowing American citizens and companies to own resources obtained from space. The door to lunar mining swung open. Luxembourg, the UAE, and several others soon passed similar laws. International law had not yet drawn clear guidelines, but these nations chose to write their own, filling in the parts the 1967 treaty had left undefined. This sparked a major debate. Was this a bold step forward, or a quiet breach of an unspoken boundary? The conversation intensified again in 2020 when the United States introduced the Artemis Accords. Formally, these agreements are bilateral arrangements between the US and each country that joins the Artemis program. But in practice, they have become a shared framework shaping the future of space resource activity. The accords allow the extraction of space resources but require transparency, cooperation, and mutual respect. They also propose safety zones, areas where others should not interfere to avoid collisions and hazards. Although not international law, nearly 30 nations quickly signed on, making the accords the strongest emerging voice in defining the moon's future. But not everyone agreed. Russia and China refused to join, criticizing the idea of safety zones as disguised territorial claims, as if marking off land and saying, "Stay out." Instead of Artemis, they launched ILRS, the International Lunar Research Station, inviting other nations to participate. The moon thus became the arena for two competing models: the US-led Artemis coalition on one side, and the Russia-China ILRS partnership on the other. And beyond these two poles, new players such as India, Japan, the European Union, and many others are stepping forward with growing influence. This race is nothing like the one in the 1960s. Back then, the goal was simple: who would set foot on the moon first? Today, the question is who can stay longer, build more sustainably, and extract resources more effectively. It is no longer a symbolic race, but a strategic one, spanning science, technology, economics, and even military considerations. What makes the race even more sensitive is the uneven distribution of lunar resources. Not every region has water ice. Not every crater holds helium-3, and certainly not every patch of regolith is suitable for building. As a result, Golden sites like Shackleton Crater, Cabeus, and the near-permanent peaks of sunlight near the South Pole have become targets for multiple nations at once. Yet current law offers no clear guidance on who has the right to establish a base first, or what happens if two expeditions choose the same location. The Artemis Accords recommend notifying others of planned activity areas and creating safety zones to avoid interference. But to some nations, this feels like creating areas of influence, contradicting the idea that the moon belongs to everyone. And once real mining begins, it is almost certain that commercial disputes will follow. If a private company extracts water or metals, will other nations recognize its ownership? If not, how will conflicts be resolved? The answer may lie in a new international legal framework, rules written specifically for the age of space resource extraction, preserving peace and fairness without stifling innovation. It might be an additional protocol to the 1967 treaty, or a new global institution, something like a United Nations Space Resources Authority. But until such laws are refined, the race continues. Nations keep launching spacecraft, testing robots, signing agreements, and expanding their influence. The moon, once a symbol of quiet stillness, has become the strategic chessboard of the 21st century. And woven through the debates over law, competition, and national interests is another force we cannot overlook: the growing presence of private actors, companies that are claiming an ever larger role in space exploration. Their story and the rise of commercial expeditions to the moon will form the next chapter in humanity's unfolding journey to this silver world. Even though debates over lunar law and the rights to extract resources still contain many gaps, a new trend is rising quietly yet powerfully, one that is already shaping the future. Not only nations, but private companies are beginning to carve their names onto the map of space exploration. And as international law struggles to keep up, it is the private sector that has become the driving force pushing the moon race forward faster than ever. Now let us open the next chapter of this journey, an era in which small companies on Earth dare to dream of placing their technological footprints upon a vast silver world, wider than any desert humanity has ever known. It feels almost surreal that only a few decades ago, the moon was a destination reachable solely through the efforts of superpowers. The Apollo era stood as a symbol, a testament to national capability, a time when landing on the moon was something only the strongest governments could attempt. But the world has changed. Technology has changed. And perhaps most importantly, humanity's mindset toward space has changed. The ambitions of private companies, lean, quick, flexible, and willing to take risks, have opened a new era many have called the golden age of commercial lunar exploration. Instead of NASA, Roscosmos, or CNSA standing alone on the stage, we now see Astrobotic, Intuitive Machines, ISpace, SpaceIL, SpaceX, Blue Origin, and a constellation of new names rising into view. One of the most defining moments of this new era arrived in February 2024, when Intuitive Machines' Nova C lander, Odysseus, touched down successfully on the moon. Scientists across the United States described it as the moment America returned to the moon, but in a remarkably different way. This time, it was not NASA, not the government, but a commercial company. Odysseus became proof that private industry can accomplish what once belonged exclusively to national agencies. Behind this success were many attempts that stumbled but held enormous value. In 2019, Israel's Bereshit spacecraft crashed just moments before landing, mere hundreds of meters above the lunar surface. In 2023, Japan's iSpace Hakuto R Mission 1 met a similar fate. Yet these failures did not slow the race. Instead, they offered precious lessons, fuel for improvement, refinement, and the arrival of new players eager to try again. The world began to understand. Failure is no longer a boundary. It is a catalyst for progress. And when speaking of private spaceflight, one name inevitably rises to the forefront: SpaceX, the company that transformed the very nature of rocket launches. With its reusable Falcon system, the cost of reaching orbit plummeted, turning once distant dreams into attainable goals. But the project that now captures global attention is Starship, the towering spacecraft taller than the Statue of Liberty itself, designed to carry hundreds of tons of cargo and more than 100 people. NASA selected a Starship-based design for the HLS lander in the Artemis III mission, which aims to return astronauts to the Moon. If Starship becomes fully operational, the cost of reaching the Moon could fall into the realm of commercially viable, a point where private companies no longer need government budgets to fund each mission. And that marks a profound turning point. When a destination becomes affordable, an entirely new economy forms around it. Lunar tourism, refueling depots, in-space manufacturing, hotels on the Moon. Once science fiction, they are beginning to shift into the realm of when, not if. But SpaceX is not the only one chasing this vision. Jeff Bezos's Blue Origin is advancing steadily with its Blue Moon lander and its national team, which includes long-established aerospace giants like Lockheed Martin and Northrop Grumman. After losing the first HLS contract to SpaceX, the national team returned and won the second contract for Artemis V. This opens a future in which multiple private companies might serve as lunar lander providers, much like several airlines sharing the same airport. Beyond these giants, a diverse ecosystem is taking shape. Astrobotic is preparing its Peregrine lander. Firefly Aerospace is developing Blue Ghost. Rocket Lab is building its Photon platform for smaller missions. Everyone wants a piece of the Moon market, a potential industry valued at tens of billions of dollars in the coming decades. What's remarkable is that space privatization has brought a rare degree of competition, and where competition exists, innovation thrives. The variety of companies, strategies, and design philosophies has created a constant current of new ideas. Costs fall, research accelerates, and clever solutions emerge. Today, even a small company with a modest budget can attempt to build a lunar lander, something unthinkable in the 20th century. However, woven into this excitement is a layer of responsibility. Space cannot become a place without oversight. Competition cannot be allowed to escalate into conflict or environmental harm to the Moon. Governments, international organizations, and the companies themselves will need to collaborate closely to ensure operations remain safe, peaceful, and sustainable. The privatization of space does not mean lawlessness. It must be a balance between creative freedom and disciplined governance. And as we look toward the future, people have begun imagining new kinds of names. The SpaceX of mining, the Hilton of the Moon, the UPS of space logistics, the Tesla of robotic exploration. Such ideas may sound distant, but considering how much has changed in just the last 10 years, we may be closer to that future than we realize. The era of lunar exploration is no longer defined solely by governments in gleaming white spacesuits bathed in sunlight. It is now an era of diversity, of young companies, bold ideas, and a new economy quietly taking shape. And in this flowing tide, every technological advance, every lander, every success or failure contributes to a story humanity is writing together. the story of turning a cold and distant world into the next chapter of civilization. From national competition to commercial rivalry, the moon has become the meeting point of countless strategies. But beneath all the contracts and disputes lies a deeper question, one that matters more than any deal or claim. When humanity finally lives on the moon, what will keep people safe in such a harsh and unforgiving world? The answer awaits in the next chapter of our journey. From the bold advances of the private sector, a new picture of space exploration is slowly coming into view. No longer just a race of companies or technologies, but a foundation upon which nations redefine how they cooperate, connect, and establish their presence on the moon. And right at the crossroads between commercialization and traditional exploration, a symbolic program of humanity is stepping into the center of the stage. That program is called Artemis, a promise to bring humans back to the moon in a way that is broader, more sustainable, and more collaborative than ever before. Whenever Artemis is mentioned, people can almost feel the quiet yet powerful continuation of Apollo, as if a story left unfinished more than half a century ago is finally being written again with new chapters full of hope. Artemis is not merely a return to the moon. It is a vision for a new generation of exploration, one in which humans do not just touch the surface for a few fleeting days, but learn to live, work, and maintain long-term activity there. Artemis the Fern, launched in 2022, was the first test of that vision. The uncrewed Orion spacecraft traveled around the moon and returned safely to Earth, proving that the SLS rocket and Orion capsule were capable of carrying the missions ahead. A test steeped in the quiet of space, yet one that confirmed the path back to the moon had been opened. Artemis the Sun, scheduled for 2024, will send a crew on a journey around the moon, the first time since 1972 that humans will travel beyond low Earth orbit. Among them are new icons of the era: Christina Koch, the woman who holds the record for the longest continuous time in space; Victor Glover, the first African-American astronaut to venture on a mission beyond Earth's immediate neighborhood; and Jeremy Hansen, the first Canadian to orbit the moon. They are seen as trailblazers, refining procedures and preparing for the most important mission: Artemis III. Artemis III is the great dream of the entire program, the moment when humans return to the lunar surface, this time at the South Pole. It will mark the first time in history that humans set foot in a region where sunlight grazes the horizon, where darkness and water ice have coexisted for billions of years. The mission will use the Starship-based HLS lander, delivering 2 astronauts to the surface for about a week to conduct geological surveys, collect samples, and search for traces of water ice, the most essential resource for humanity's long-term future there. The focus on the South Pole is no coincidence. It holds permanently shadowed craters and the largest known potential reserves of water ice on the moon. If identified and extracted, this resource could open an entirely new chapter: self-sufficient fuel production, oxygen generation, and potable water. The absolute requirements for maintaining a long-term base. For this reason, the Artemis Base Camp is being planned as humanity's first outpost on the lunar surface, expected to take shape in the 2030s. But perhaps the clearest symbol of Artemis is not the spacecraft or the hardware. It is the way the world is building it together. The Lunar Gateway, a small station orbiting the moon, is the living embodiment of this cooperation. Though smaller than the ISS, its strategic importance is immense. A bridge between Earth and the lunar surface, a place to rest, refuel, coordinate experiments, and prepare for landings. Notably, Gateway is not the creation of a single nation, but of many. Canada is providing the Canadarm3 robotic arm, a more advanced successor to those that served the ISS. Europe is supplying the service module and the IHAB module, the heart of living and research functions. Japan is ensuring logistics, cargo deliveries, and may contribute to habitation systems. The first gateway modules are expected to launch in 2025-2026. This model of cooperation not only shares cost, but strengthens international ties in an era where space exploration is no longer a two-sided race like in the Cold War, but a dynamic, multipolar network. Meanwhile, back on Earth, many nations are also accelerating their lunar ambitions. China continues its successful Chang'e missions, landing on both the near side and far side, and returning samples. They are working with Russia to build ILRS, an international lunar research station, positioned as a counterpart to Artemis. India, after landing Chandrayaan-3 near the South Pole in 2023, became the fourth nation to achieve a soft landing. The UAE has sent the Rashid rover. South Korea's Danuri orbiter is gathering invaluable data from orbit. Altogether, these efforts show that the Moon is entering a new age of prosperity, a period where cooperation and competition intertwine in ways never seen before. Much like seafaring once pushed nations to expand their horizons across the oceans, the Moon now stands as a second ocean, where every nation hopes to be a pioneer. Within this vast landscape, Artemis serves as a guiding lighthouse. Not a single beam of light, but the combined glow of many nations illuminating the future of a second world humanity is preparing to enter. And as each piece of Artemis falls into place, a larger question gradually appears. If humanity can cooperate to open the lunar era, can we also build a sustainable community there, one that truly belongs to many nations at once? That question will lead us to bolder predictions about the future of humanity's presence on the Moon. The story of the next chapter. Amid the vast tapestry of international cooperation that Artemis is weaving around the Moon, a natural question begins to rise. When humans no longer stay for a few brief days but begin to remain for longer stretches, how will we actually live in that silent, frozen, distant world? From the foundations laid by Artemis and the Gateway, the prospect of settling on the Moon is slowly shifting from science fiction into a story being written through very real preparations. So let us open the next part of our journey, the life humankind might lead when the very first homes appear on the Moon. In the decades ahead, if all plans unfold as hoped, humanity's first outposts will likely rise near the Moon's south pole, close to Shackleton Crater, a place blessed with two rare gifts: months of continuous sunlight and the presence of water ice lingering in nearby permanent shadows. NASA envisions the Artemis Base Camp as a first village on the Moon, composed of three core elements: a fixed habitat capable of housing 4 people, an unpressurized rover for short-distance travel, and a mobile pressurized rover, something like an elongated rolling home, allowing crews to travel tens of kilometers while maintaining full pressure and life support inside. In the early years, each mission may stay only a few days, gradually extending to several weeks. The long-term goal is to support stays of 1 to 2 months. To enable life on such timeframes, the base will need a strong, stable power system. Current designs propose about $100 kilowatts of total energy, provided by solar panels placed on sunlit ridges and supported by a small nuclear reactor. Alongside this will be a communication station, supply depots, repair facilities, and a compact laboratory. Yet these homes must withstand a far more dangerous environment than anything on Earth. Protecting humans from radiation and micrometeorite impacts becomes the top priority. Ideally, part of each habitat will be buried below ground or covered with 2 to 3 meters of lunar regolith, a natural shield from radiation and cosmic dust. Many concepts use inflatable modules that expand and are then covered with soil, creating spacious interiors while remaining safe. Inside, the living environment is kept close to Earth-like conditions. Pressure around 1 atm, temperatures near 20 degrees, controlled humidity, and artificial lighting designed to maintain healthy circadian rhythms. A crucial part of life on the Moon is dust control. Habitat entrances require decontamination chambers with air jets or electrostatic systems to shake off clinging dust. Some designs propose suit ports, spacesuits attached to the outside of the habitat that astronauts enter from the rear, reducing dust infiltration almost entirely. Daily life brings its own challenges. Providing enough water, food, and air when resupply cannot be as frequent as on the ISS. Water will be extracted from harvested ice and purified. Air will be recycled thoroughly. CO2 removed, oxygen replenished from reserves, or produced on-site by extracting oxygen from regolith. In early years, food will mostly be packaged and shelf-stable, but gradually, lunar greenhouses will appear. Experiments on Earth have shown that lunar soil samples, once treated and enriched, can support leafy vegetables. The first lettuce grown on the Moon would not only provide fresh meals, but serve as a quiet symbol of human resilience and adaptability. Meanwhile, spirulina algae could be cultivated in tanks, absorbing CO2, producing oxygen, and offering a rich protein supply, forming a tiny closed-loop ecosystem within the base. Even with such amenities, living on the Moon will remain physically demanding. With gravity only 1/6 of Earth's, muscles and bones weaken quickly. Astronauts will need to exercise at least 2 hours per day, using tethered treadmills and resistance machines to slow the loss of bone and muscle. Radiation, even with shielding, will accumulate over time, placing natural limits on how long crews can stay, much like the 6-month limit aboard the ISS. Emotionally, isolation is an equal challenge. Outside the habitat lies only endless gray terrain, a sky black as ink, and days and nights that each last 2 weeks, a setting that easily disturbs natural sleep rhythms. Lunar bases will need emotional medicine, entertainment rooms with music, films, and books, quiet spaces lit with Earth-like lamps, and high-speed internet for conversations with loved ones. With only a 1.3-second delay, video calls remain almost seamless, a soft thread connecting two worlds. Life on the Moon will be busy. Beyond maintaining the base, crew members will extract ice, service equipment, and conduct a wide array of experiments. The Moon is a natural laboratory. Biology in low gravity, 3D printing in vacuum, metal production on-site, and especially astronomy. The Moon's far side, where Earth never rises, is an ideal location for massive radio telescopes untouched by atmospheric or artificial interference. The Moon also offers the promise of exploring ancient lava tubes, vast underground chambers with stable temperatures. If habitats are placed deep within these caves one day, humans could live far more safely. Remotely operated rovers might travel hundreds of kilometers to survey terrain, hunt for minerals, or expand our maps of the lunar surface. Once production techniques mature, metal refining, regolith brickmaking, oxygen extraction, the Moon will begin developing a basic industry of its own. At that point, an outpost stops being temporary shelter and becomes a small community, the first seed of an off-Earth civilization. Living on the Moon is a tremendous challenge, but also a quiet promise. A promise of a future where humanity does not merely gaze at the sky, but begins to build a second home amid the silent darkness of space. And as we imagine that future, one final question begins to take shape. All the dangers, the mysteries still unsolved, and the trials the moon sets before us. What hidden secret are they leading us toward in the most perilous place on this silver world? The answer awaits in the final part of our journey, as we imagine the first residents living in pale, dust-coated habitats near the icy lunar poles. We begin to realize that the challenges they face are not just stories of survival. They are stepping stones lifting humanity beyond the boundaries we once believed unbreakable. And from this vision of ordinary life in an extraordinary place, a gentle yet profound question rises. Where will all these efforts lead us in the long, unfolding journey of the cosmos? The answer comes now, as we close our travels through the moon's most dangerous landscapes and turn our gaze toward the wide future ahead. For thousands of years, the moon has symbolized distance, mystery, and permanence. A place humans could only dream of, a canvas for fairy tales and poetry, quiet and unreachable. But in our century, what once seemed impossible has begun to take shape. From those eternally shadowed, bitterly cold craters, the places once seen as dead zones, tiny sparks of hope now appear. Ancient water ice, rare organic molecules, and resources capable of igniting an off-Earth economy. The harsher the place, the greater the reward. That is the rule of nature and the engine of science. Had no one dared to enter those frozen, pitch-black regions, we would never have known that the moon could offer drinking water, oxygen, rocket fuel, or minerals needed to sustain a long-term human presence. Thanks to robotic explorers and the brave astronauts who will follow them, the impossible has begun to turn into the achievable, opening a new doorway into humanity's second era of exploration. Yet these achievements do not come merely from courage. They grow from the unending spirit of discovery, the same spirit that carried humans across forests, deserts, oceans, and eventually into space. The journey back to the moon today is not only a demonstration of technological skill, it is a reminder that human curiosity and ingenuity never stop. From surviving a few days on the moon during Apollo, we have progressed towards staying for weeks, then months in the Artemis era. And in the future, humans may remain for a year or more, producing water, oxygen, and food right in the harshest environment we have ever dared to enter. NASA has often said that learning to live and work 240,000 miles from Earth prepares us for an even greater goal, sending humans to Mars. Indeed, the moon is no longer the destination. It has become a training ground, a place to practice, to test, and to prove that humanity can live far from home for extended periods. If the Artemis base camp becomes reality, it will be the first full model of off-Earth settlement. Local resource production, high-tech agriculture, closed-loop recycling of air, water, and materials, and long-term health in low gravity. But beyond these grand plans, the moments that touch people most deeply may be the smallest ones. Imagine this. One night, as you look up and see the gentle glow of the moon hanging in the sky, you know that it is no longer a lifeless world. Perhaps the faint glimmers your eyes catch are not reflections, but the tiny lights of a settlement. Maybe only 4 or 10 people, living inside a regolith-covered habitat, sharing a simple meal grown in a lunar greenhouse, or preparing for an EVA into the darkness to collect fresh samples of ice. These images may sound like distant dreams, yet every great human achievement begins exactly that way. From Apollo 11's landing, to Artemis exploring the South Pole, to building rovers that can survive the eternal night, Each step adds a piece to the future we are slowly assembling. And when we close this journey, the most beautiful part is not the list of scientific data or mission names, but the quiet reassurance that humanity still moves forward. Even though the moon is full of danger, it has become a symbol of our courage, creativity, and endurance. The universe is vast and deep, but the first steps on the moon are teaching us how to reach worlds far beyond. Now, as you close your eyes in the quiet of the night, imagine standing on a silver-gray plateau, watching Earth rise gently over the horizon. A small blue world turning in the darkness, holding your home, your friends, your familiar life. Believe that no matter how cold the moon may be, human intelligence and courage will shape it into a second home. A place where today's dangers will become tomorrow's stories, told to future generations. Wishing you a peaceful night. Let sleep carry you softly through the stars, where every dream can open a new horizon. Sleep well, wrapped in the faint hum of the boundless universe.